Welcome back to my Billet intake manifold build series. I'm teaching you how to build an intake manifold like this from start to finish, from design all the way to machining. If you're new here, go back to the beginning of the series and start there. I don't want you to miss any of the information I'm sharing there. If you're not new here and you've been following along, let's get back into Fusion and get going. I have an absolute buttload of time into this project, so please support the channel, hit that subscribe button. Welcome back, guys. I got a few questions, so let's get straight into it. First question I got is 3D printer related. Somebody asked about the material I used, the 3D printer I used, and how I got the print accuracy to prototype this manifold. The material I used was just cheap PLA, which is probably the best material in my opinion when you're just prototyping a part for fitment. You can make it fairly accurate and it doesn't have a lot of shrink down. It's also cheap. I'll give you a quick overview of the 3D printer I used after we get through these questions. And as far as the 3D print accuracy goes, that's kind of a huge subject and deserves at least its own video, if not its own series. There's a ton of information out there on YouTube about that subject, so you can go find those if you need to, if you don't want to wait until I get into it. But we will be getting into it in future videos. Somebody mentioned I should get a space mouse. Ironically, I already have one. I just don't like it. What a space mouse is a secondary mouse for 3D modeling to be used in conjunction with your normal mouse. And it gives you the ability to pan and zoom and rotate your objects with your left hand while still using all of your other functions with your right hand, with your normal mouse. I tried to use one for a while, but the way I have my Fusion set up, I just find it faster and easier to do with having the orbit on the center mouse wheel when you push it down, and the zoom is on the center mouse wheel as well when you rotate it. So it's set up in a SolidWorks fashion. I also have my zoom in and out reversed. You can do all of that in preferences. So if you guys like the freedom of movement I have with rotating the models and stuff, go into your preferences, go down to your mouse settings and check the SolidWorks function. And you can even try reversing that mouse wheel zoom as well. Let me know what you guys think about that. A couple of people have pointed out that if you extrude through a body and you have a protrusion that you want, you can just select it and delete it. That is true in some cases, but I've found it to be not that reliable, and that's why I showed you guys how to extrude in little bits at a time so that you can avoid using that not so reliable feature of being able to delete those protruding features. I'm not sure why it's unreliable for me. I'm sure it has something to do with the complexity of the geometry that it's protruding through, but I've even had it not work on some pretty simple geometry, so I just don't trust it, so I try not to use it. Somebody asked if the extrude to object feature would be better in some of these cases. And I did cover that in one of the videos where I was extruding to a surface or to a body, but there are cases where that doesn't work. Namely, I remember making the injector platform here where the injector hole goes through. Because when I drew this, there was already part of the sketch inside of the body, that extrude to body won't work or extrude to object won't work. And if the surfaces are too complex, it also will fail for some reason. So that's why I try to choose to make all of my external features before I cut or shell out the inside of the part. Somebody asked if I was getting custom O-rings made for my O-ring grooves. A lot of the O-ring grooves on this part can use like a standard size O-ring, but for the long skinny grooves, like between these two surfaces, I'm using standard O-ring cord. So you cut it to length yourself, and for me it's been highly reliable, but there's some tricks on how to install it. I'm going to show you that now, and then I'll go show you my 3D printer setup. So on this part, this is what I'm using. This is a 1/16 silicone cord stock. So its actual diameter is 0.070, so 70 thou. And I just cut myself an extra long piece. Now when you're doing this, you want to make sure that the end you start with has a nice square cut. So I'm just going to trim this so it's nice and square. And then I'm going to pick a spot on my O-ring groove. I'm going to pick over here at the end because it has the least amount of curve. The rest of this stuff is pretty curvy. So I want the end to be over here on the least amount of curve. So when you're installing this O-ring, you just want to lightly set it into the groove. You don't want to stretch it or compress it at all. Just really nicely just tap it down into the groove without pulling on it or really squishing it in. And now that I've gotten to the end, I want to put this right in to where it starts. I'm going to cut this O-ring about a 1/4 inch long with a nice square end again. So now basically the ends overlap about a 1/4 inch. They're not going to overlap though, because I'm going to take this end and I'm going to start it where the other end starts. And then I'm going to kind of work backwards, squishing this O-ring and kind of compressing it just a little bit as I put it in the groove. And this will help it to take up that extra length. And now that I have that in the groove and it's kind of compressed at the ends and all the way around, when you bolt that top piece down and it compresses that O-ring further, it's going to shove that end together and it'll seal perfectly. We do this on vacuum fixtures all the time and it works great. If you are nervous about it, you can put a little dab of like silicone RTV right at the end of the O-ring, but I found that it's not necessary as long as you use this technique. So there you go. And the end is right here, and you can barely even make out that it's there. And it'll seal up just fine when we bolt that top down. All right, guys, let's go check out my 3D printer setup. So here's my little print farm. This is actually my daughter's Ender 3 that she never uses, so it just sits out here. And then I got the Bamboo, great machine, but isn't obviously big enough to print this manifold on. So this is my custom built Folgertech FT6. It's a pretty large build volume, and this is what I printed the intake manifold prototypes on. It's got a work envelope of 750 millimeters, 350 millimeters deep, and 400 millimeters tall. Pretty good size work envelope. It's custom built off of a Folgertech kit, but I've done a lot of custom things to it after that. It's running on a Duet Wi-Fi board. I've got a completely custom tool head that I built for it, all designed by me, custom cabling, active chamber heating, and it's just generally been upgraded quite a bit. And I'm actually getting ready to build a whole nother 3D printer. Those of you who dabble in the space probably know what that is, but we'll be diving into that world in future videos. And the last question I've gotten a multitude of times is, when will the first cam video be launched? Well, the answer is right now, so let's go. All right, guys, we're getting into the first of the cam side of this intake manifold. So let's get into Fusion here. Let's go through my initial setups here. So in the first video, we talked about how I modeled the stock. So here's the lower runners and the modeled stock. Part of the reason I modeled the stock was because I needed to do a material prep on it so that I could bolt it to my trunnion table. So this is the lower runners and the stock. So you can see that I have threaded holes here in the stock, and that's so that I can bolt through the trunnion table and into the raw stock of the part. I also have the trunnion table itself designed into this. You can see how I intended on holding the raw material on the trunnion table. I don't have my whole fourth axis and everything modeled because I did it in previous software. I'll have to go in and do that one of these days so I can do avoidance and things like that. But for now, this is what I have. So on this initial part, I have two setups that I did initially here. So I just basically did a facing pass, I drilled the holes in it, and I tapped the holes in it. And then I did the same thing for the upper runners. Modeled stock, threaded holes in the stock, and I did basically the same material prep on that. So it actually uses the same exact bolt pattern as the first, as the lower runners stock. That way, I only have to make the one trunnion table. It's a symmetric bolt pattern, and I basically can hold both of those blocks of material. Even though they're slightly different size, I can hold both of those blocks of material on the same bolt pattern on the trunnion table. So that's my material prep operations for both the upper and lower runners. And then I did the trunnion table. Just had the bolt pattern in that. It's just a 1x4 chunk of aluminum, and I just did the through holes there. And then I also did a counterbore here so that I had a point where I could touch off the center line of this part, and it would always be the same. So I can touch off in that bore for my x-axis. Let me open up this sketch here. And then I had this sketch back in the design side, and this represents the center line of my A-axis, so my fourth axis. And when I did these setups for the trunnion table, as well as the actual operations on the upper and lower runners, I can use that sketch to designate my Y and Z axis center line. That sketch is also centered on this bore, so that's how I designate my X axis, and it aligns with that sketch. My work coordinate system origin is right on that sketch. So that ensures that all my parts stay consistent and located in the same location. So that's my initial setup, material prep on two different parts, and then my trunnion table. This construction line here is the center line of my axes, so my A axis in both Y and Z, and then this center line is the center line of my X axis. So on my machine, this XY is always set to a number that's touched off to my A axis, center line of that. So that never changes. The only thing that can really change is the X axis location. So that's why I made this pocket in there. And that way I can, if I have to set these up in the future, I have that X axis location, easy to touch off on. My Y and Z are always the same. And I keep those numbers in the machine in the higher work coordinate system. So like G59 and that I don't typically use. If I need to use them, I can just write them down and then punch them back in, but I keep them in there so that I can just copy them to whatever work coordinate I'm using. In these, I only use G54 for the entire part. So I just copy the numbers that I have in that G59 into G54, and it knows where the Y and Z axis are located, and then I just touch off the X axis with the probe or edge finder if that's what you're using. So we did the stock prep, and then we do the trunnion table, and then we bolt the material to the trunnion table. So this is my first operation on the lower runners, which is what we're going to cover today. Okay, so let's go through the first toolpath here. So the first toolpath, I'm doing an adaptive roughing toolpath. Basically what adaptive is it's a 3D rough based on your solid model. So it's more efficient because you can take larger step downs and then it only does finish cuts on the step ups. You can see that I'm using a fairly long 1/2" end mill with a custom designed holder that's one of my shrink fit holders that I custom designed in Fusion so that I could use it for avoidance. And then I just let the 3D adaptive do its job. Set up the parameters. We can look at those real quick. So you can see that my geometry is the stock outline, and then I'm doing a 1" step down and a 50 thou step up. So it calls it fine step down, but it's really a step up from your roughing step down. And I'm leaving 20 thou everywhere for cleanup. I did add smoothing because it makes my program smaller for the actual G-code output. And I'm making sure that I have my linking heights high enough to where this trunnion can rotate between operations without a tool crashing into the part. So this is really important. Make sure that your clearance height is well above the part. In this case, the center line's way down here. So this 2 inches above the actual solid is plenty. So that's the first operation. If we get into this next operation, you can see that I'm doing it from a different angle. So if we open that, the only thing you need to do, it's basically the same adaptive roughing toolpath, except that I'm using rest material instead of stock material. So in the geometry here, I'm using remaining stock. So it's using whatever's left of the material that's already been machined from the previous operation, which is here, previous operations. And I'm ignoring stock less than 25 thou. That way, hopefully it will take that 20 thou that I left and not try to remachine all those areas. So hopefully saving some time. And then all you have to do to go from this different angle is you set up your tool orientation. I set up my tool orientation. So check that little box. And then I just picked a plane that was the direction that I wanted the tool to come from. So I believe I picked the top surface of this trunnion table here. Oh, and also I have shaft and holder selected here on the tool. So it basically uses clearance to avoid the model or the fixture. In my geometry selection here, I have the fixture selected as well. So you can see that the trunnion table is selected as the fixture and the model is selected as the model itself. So the toolpath is able to avoid anything that it could crash into when it's doing that toolpath, even though we're going a deeper depth where it would actually engage that trunnion table if you didn't avoid it. So, and then pretty much same parameters. Looks like I'm doing a little bit larger roughing step down on this one. I think the previous one, I kind of split the difference on the depth I wanted to go. So it would only do 2 full passes. And then on this one, it's doing a little bit larger step down with the same step up, or fine step down is what they call it. And then stock to leave is 20 thou everywhere as well. Smoothing on, all of that stuff. Oops. Gotta wait for my computer to regen all this crap because I hit OK instead of cancel. Oops. So on that note, generating these toolpaths can take quite a while, especially when you're using rest material. The software has to go in and calculate all of the remaining stock before it even starts calculating the toolpath, which can take quite a while, especially when you initially generate these toolpaths. Once it's generated and you just make small changes, it typically happens a little faster, but it can take a hot minute. So what I like to do is generate the toolpath with almost none of the optional little buttons clicked, like reducing air cutting or keeping the tool down or anything like that, to get the tool path to generate as quickly as possible for the first time. And then you can go back in, make your adjustments to save time and reduce air cutting and keep the tool down and things like that, and then regenerate the tool path. And it'll typically happen a little faster than if you had all of those features selected right off the bat when you initially generate the tool path. It can be very computational heavy, so a better computer helps a lot. I'm working on a laptop, which is a little bit slower than a desktop of equal power would be. But Fusion typically uses single core processing. So even though I've got 32 cores or whatever, it's only using one of those cores per toolpath, from my understanding. So if you're looking at computers to do CAM in Fusion, maybe look at the single core performance of the processor itself, because the way I understand it, that's what's most important when calculating these toolpaths in Fusion. Okay, this is still calculating these last few toolpaths. It's been almost 15 minutes, but we've got a couple here we can look at. Problem is all these following toolpaths, there's about 5 of them after the one that I clicked OK on, and they all use rest material. So they all need to recalculate because I clicked OK on this one up here. So going on 15 minutes here and it's still only about half done. Note to self, try not to do that again. We'll see if I can get through the rest of this video without accidentally clicking OK again. So anyway, here's that second adaptive roughing toolpath, and it's using that tool orientation from this direction. The trunnion table is rotated up at 90 degrees. Then my next toolpath is rotated the opposite way. Basically all the same settings, all the same selections for the trunnion table as the fixture and the part as the model. So you can see what we have so far. And then I wanted to get the roughing in a little bit deeper in a few spots here. So I went from an angle. So when you set up this tool orientation, you can select faces or planes, and then once you do that, you can grab this handle here and you can rotate that tool orientation to wherever you want it. So in this instance, this selection here of this face worked to get that angle so I could get down up against this flange here with the roughing. So I just selected that plane for the tool orientation. Basically all the same settings here. We have our fixture selected, our model selected. We have our roughing step downs at 1.25 inches and our fine step down at 50 thou, and we're leaving 20, and we have smoothing turned on, and our clearance heights are still plenty high to be able to rotate around this part. So you can see that I'm just working my way around this part with different tool orientations to rough out all of the material. Even though I have a bunch of undercuts here, I'm using the 4th axis to position this part so that I can get the tool into the locations that I need to in order to rough out that material. Okay, so we've got a couple more of these calculated. There's just one left it's working on. Should be done by the time we get there. So there's that tool path, and then I did the same thing on the other side. So you can see how much I've roughed out now. I've got pretty deep pockets in there, plenty to get the ball nose plus the radius of the ball nose down in there to finish this side of the part. And then I did the same thing on that other side, and then I did it at an even steeper angle so that I could get under this flange area here, get to the back side of those runners and rough out under there so I could finish that in this operation as well, because on the next operation I won't be able to get to this undercut from the other side of this part, so I need to be able to finish a lot of this part in this operation. Then I did the same thing on the other side here, so you can see the pockets there. And then I did some angled roughing of the insides of these ports. So selecting the outer chain here as my boundary, and then roughing out what I could with this short end mill from this side of the part on both sets of runners here, so from different angles, so you can see how I'm getting the tool in there. And then I'm even cutting from the bottom side here and roughing that port in there. And you can see I'm cutting through a little bit here, but I still have material down in there. So I did that from both sides, just using tool orientation to position the part. And then before I switched tools, I went and I faced all of these flat areas that I could. So just doing a facing pass across them. There was some avoidance that I had to do with the trunnion table and stuff here. And then I actually contoured the outside of this flange. It's a square edge. So just using a 2D contour toolpath and shortening the toolpath so that it wouldn't hit the trunnion table, because it doesn't have a tool avoidance available on that 2D toolpath. But you can do that manually just by shortening your chain and just making sure that it actually avoids the fixtures or what have you. And then I faced the little face of the fuel rail mounts, faced the top of the part, faced the fuel rail mounts on the other side, faced the other side bottom of the flange, and then did a contour around that side too. So you can see that a lot of the flat surfaces are now finished on the part, and I've got a ton of the roughing done. There's just a little bit I need to get down in this port still, but I needed a longer tool for that. So then I used this extra long end mill to reduce shank end mill with just the flutes on the end, solid shank. And I used that to go in and rough the rest of the port. So from both the top sides, there's those two, and then from the bottom side. So going through the bottom of the port here to finish roughing out as much as I could get of that port. So you can see that I positioned this part on the trunnion so that I could finish this entire inside of the port in a single operation. That way I wouldn't be relocating the part and have possibly blend lines that don't match and things like that, because I am going to have to finish these ports from both sides as well, because they're not just taper, they're also angled. If you can see there, the beginning of the port's here, the exit of the port is down here. So there's actually an angle to them, as well as the radius of them. They curve up at a radius, and they have taper. So this is a different shape at the top than it is at the bottom. So it's a pretty complex geometry. That's why I positioned this part on the trunnions so I could machine from both sides of this port in order to reach the entire inside of the port. So I roughed that from the other side as well. And you can see that there's a small step left in there, but the majority of this port has been roughed. Now is where we get into some simultaneous 4th axis machining. A little caveat to this: you have to have the manufacturing extension in Fusion to be able to do simultaneous 4th and 5th axis machining. I'm doing this entire thing on a 4-axis because I don't have a 5-axis machine, but everything up until this point has been positional, and you can do with the basic seat of Fusion without having to have the manufacturing extension. But the toolpaths I use coming up here, you do have to have the manufacturing extension. So theoretically, these toolpaths could be done positionally. It would just take a lot more work, and they probably wouldn't come out looking as smooth as they do when you can do simultaneous. Okay, so now we're going to finish the insides of these ports. So what I use for that is geodesic, and I'm using this extremely long 1/2-inch ball end mill, which is very difficult to keep it from chattering and things like that. Had I had a different tool available that I could have undercut with, like a lollipop style mill, or you'll see in upcoming videos I actually made my own tool for doing the upper runners, but I didn't have anything like that for doing this, so I was kind of forced to use this extremely long end mill. It was a bit difficult to get the finish to come out how I wanted, but this is what I did to get it done. You can see the toolpath down in here is doing a curved geodesic toolpath that's following the port. So let's take a look at this toolpath here and how I drove it. So you can see that I have a circle drawn out here in space at the rough angle of the port. And this was what I used to control the tilt of the tool. So if we go into the multi-axis tab here, I have 4-axis machining selected. I have my X-axis set up as my axis of rotation. So rotary axis is X-axis. The rotary origin is the work coordinate system origin. The tool axis is from a curve, and the guiding curve is this sketch here. So this circle. And I have collision avoidance selected. So you can see that this axis is limited to within this circle for the center line of the tool, and the tool has to be driven from that location. So once you select your 4-axis machining, you no longer have tool orientation control. You basically have full freedom of movement on that A axis, and you have to be able to limit it to where you want it to move. So that's what this arc is doing. And my geometry is the inside of that port is selected as my drive surface. I have my passes set to blend, so it's basically going to do a equal step down instead of trying to go and scallop the part. That's the other option in here, is scallop, but I have it set to blend. Machining side's automatic, and then I have the entire model selected as avoidance. I have the fixture selected as avoidance, and my drive is simply the inside of that port. It's going to try to avoid everything except the inside of that port, and it's going to use this arc out here that's drawn out in space as the tool center line. If we go into the heights tab, you can see that I have the heights as a cylinder. This way it's going off of the center line axis of the rotary axis, and I have outermost of selected, and I have all of the options selected there. So the tool will retract to a clearance height greater than the entire radius of this part, so it can't collide with anything. And then for my passes, I just have a step over of 75 thou. Now this is a maximum step over, so with these geodesic tool paths, it's going to get tighter or looser step over based on the geometry because it's trying to do a blend style tool path. If you were to pick scallop, this would remain more constant. Since it's a blend style tool path, this is the maximum step over, so the greatest possible step over, and any geometry that dictates less than that and maintains that blend style tool path will be a smaller step over than that. So in general, I've found that this number can be a little bit bigger than what you intend your step over to be. And I also have spiral selected. So this is going to do a spiral tool path from the top to the bottom of that geometry, basically maintaining a distance just like you would do like a ramp or something like that. So it's maintaining a constant ramp down into this part. Now I have my tolerance set to 1 thou, but I have my smoothing set to 100 thou. In these geodesic toolpaths, you can have the smoothing set pretty high. So that's about it on that one. You can see that this toolpath is avoiding the undercut surfaces because I don't have an undercutting tool that would allow it to cut under there. And that's why I have to do this same toolpath from both sides of the part. So I did all these upper tool paths using that same strategy, and then I went and finished them from the bottom side to get the remaining geometry from this side of the undercut. So from this bottom side now, this side is the undercut instead of this side, so I'm able to machine the remainder of that geometry. Hopefully that makes sense to you guys. So I went through and did all of those from the bottom sides. And those were actually just a roughing tool path. They were still leaving about 10 thou for cleanup. Like I said, this tool is really long and it's hard to keep it from chattering. So I had to do a very minimal finish pass. So then I went back through and did all the same things, but with 0 stock to leave and a slightly smaller step over to finish all of these ports. So literally just copying all these tool paths and then giving them a 0 stock to leave instead of a 10 thou stock to leave. So that's all the ports finished. You can see how they blend really well with the model material there all the way through. So that's the inside of the part basically done. Now we need to machine the outside of the part. So I started off by doing some geodesic tool paths on these fuel rail mounts. Oh, one thing I forgot to mention on these tool paths here for the ports is I did have to play around with the direction. So both the reverse step over direction and the direction of machining in order to get these tools to climb cut. Geodesic doesn't do it automatically, like assume that you're climb cutting or conventional cutting. So you have to make sure that the tool path is doing what you want it to and machining in the direction that you want it to. So something to pay attention to there. And I had to do the same thing on all of these tool paths for these fuel rail mounts, getting that tool to start at the top and rotate in the right direction to be climb cutting and step down in the right direction instead of starting at the bottom or starting at the top. You do have to pay attention to that in geodesic to drive the tool the direction that you want. So that's all those little fuel rail mounts machined. And then I did a contour using this same shorter 1/2-inch ball mill around that upper profile to finish out the outside profile of this top flange. I had to do this with a ball mill because there's points where it blends into a radius here in the runners, and you can't do it with just a square end mill. So I did this little contour around there to finish that. And then I did a parallel tool path to start finishing the underside of this flange here. So again, I'm just using tool orientation in a positional way on all of these tool paths that I've shown you on the outside of this part so far. And all of this can be done without the manufacturing extension, just using tool orientation. So you can see that this tool's at a slight angle compared to the face of this flange here. And that's so that I could go in and finish these flat surfaces under here in a step down type of way with a ball mill. Repeated that tool path on the other side. And then I had to get underneath this top flange to finish the underside of that. So I had to go from this pretty steep tool orientation, 90-degree tool orientation, to get to the bottom side of that top flange and the part of the runner where I won't be able to reach in future operations. So I did that on both sides, and you can see that the underside of that flange is nicely finished now. Same thing on the other side. So now I have the top outside of this flange and halfway down the face of the top side of this flange, as well as underneath this lip on the lower flange, all finished. So now we need to finish this runner here. And what I did for that was I used a 4-axis simultaneous tool path. So this is using the 4th axis simultaneously with X, Y, and Z to finish this surface. So you will need the manufacturing extension to do this tool path, but again, this could be done positionally. It probably just wouldn't turn out as nice as it will doing it this way. So I did that on all the outsides of the runners. And if you want to look at how I drove that, I basically did geodesic, but I actually used guide curves here. So I actually split the faces of these ports so that they're 2 different surfaces. So I drew a surface between them, and I used split face in the design side to split those faces. And then I used the edge of that surface as my guide curve. And you can see that I have, again, the entire model selected as avoidance, except for the surface I want to machine. My drive surface is that surface that I want to machine. And I'm using this line drawn out here in space as the guiding curve for the center line axis of my tool. So the tool has to go through this line, the center line of the tool has to go through this line at all times while it's machining that surface. So that's what's guiding my tool direction, and that's how the tool path turns out. So that's about it for the hard surfacing stuff. The rest of this is just doing some O-ring grooves, some drilled and tapped holes. So I'm pocketing out the injector hole here with a little 1/4 inch end mill, cutting the injector hole through both sides. And then I did a little scallop tool path with a 1/4 inch ball end mill to finish the inside of this injector port. So a little finishing pass there. And then drilling the holes through the flange here for the mounting bolts, drilling the top flange, using that same tool to drill the fuel rail tapped holes on both sides, and then tapping all of those same holes with an M6x1 tap. So tapping, tapping, tapping. And then I did a contour ramp tool path with a little tiny 1/16 inch end mill to do this O-ring groove. And this is what I mean by it takes forever to do O-ring grooves, and that's why the OEMs don't use it, because this tool path takes way longer than you think it would. Same thing for the O-ring grooves on the head flanges. And then I'm just going through and chamfering everything with a little 1/4 inch chamfer mill. So that's about it for operation 1 on these lower runners. This is already going to be a super long video, so I think we're going to stop there and we're going to do op 2 in the next video. But you can see that every part of these lower runners is machined that I won't be able to get from the other side in the second operation. So that's about it for this video, guys. Again, I've had the shop shut down for about 6 hours now to film this video, and I'm not running parts making money, and my YouTube channel doesn't make anything. So if you're finding this content valuable at all, please subscribe to the channel, share these videos, like these videos, and definitely comment with your questions down below. I really appreciate you guys watching. We'll see you in the next video.